Hello, my name is Joe Cloud and I'm with NASA's Kennedy Space Center. On behalf of my co-authors, I am presenting our work on vision-based movement primitives for lunar hazard avoidance. Due to the high cost of launching materials to the moon, future missions will leverage resources found in situ. This is referred to as in situ resource utilization, or ISRU. This means processing lunar regolith to extract valuable minerals like oxygen. To harvest these resources efficiently, NASA is developing autonomous excavators that must navigate the terrain while maintaining high operational efficiency to excavate enough regolith to supply ISRU processing plants. One such excavator, depicted here, is called ISRU Pilot Excavator, and it uses cameras for navigation. These robots face unique challenges. At the lunar South Pole, the sun never rises more than a few degrees above the horizon, creating extreme lighting conditions with long shadows and blinding glare. Additionally, autonomous lunar excavators must maintain efficient paths while avoiding obstacles. Delays or excessive deviations will impact RSU resource gathering. Earth to moon communication is bandwidth constrained and not conducive to teleoperation due to the high efficiency goals. This necessitates robust autonomous navigation. We've developed a system that integrates vision-based obstacle detection with dynamic movement primitives. This represents one potential approach to navigation on the lunar surface. Our architecture uses closed-loop control tested against a high-fidelity, unity-based simulation of the lunar South Pole. The system publishes stereo images at 5 Hz from the front stereo cameras. The simulation environment also includes lunar terrain with statistical rock distributions based on Apollo surveyor data and is set up with a 5-degree solar elevation. Our approach uses dynamic movement primitives to prescribe robot motion. In this equation, robot acceleration, shown in blue, is proportional to the distance from the goal in green and the learned primitive movement in maroon. The system is dampened by the robot's velocity in brown for stable behavior. K and D are diagonal matrices for 2D trajectories. The forcing term faces out with the phase variable S, making it goal independent. We've added this obstacle avoidance term P, which modifies trajectories in real time based on detected hazards. Our vision pipeline generates depth maps from stereo cameras and uses YOLO V8 for rock detection. The system overlays detected hazards on the depth map and computes rock poses and heights from segmentation masks. This provides necessary input for obstacle avoidance, with rock-sized estimates being used for our weighting function. Here we show our lunar South Pole simulation camera views with overlays. The left view displays a real-time rock detection with size estimates in green labels. The right view shows the obstacle vector in blue and robot heading in red, which is used for our DMP controller. We also show this yellow line, which represents the nominal DMP trajectory. You can see how extreme shadows and lighting affect the visual environment. This is what in part makes the lunar South Pole navigation somewhat challenging. We extend the steering angle approach with a weighting function. Hazards are detected only in the forward field of the view. The weighting function considers obstacle size, which addresses the limitation in our previous work published at IROS. The equation shows how multiple obstacles contribute to avoidance behavior with gamma and beta as tuning parameters. The exponential term provides smooth trajectory modifications, while the inverse square distance naturally prioritizes nearby hazards. Here we visualize the impact of the weighting function, which balances obstacle size and proximity. Larger obstacles exert stronger influence on trajectory modification, ranging from 0 to 1. The lambda parameter controls curve steepness. We evaluated our system by comparing nominal DMP trajectories with obstacle avoidance modified paths. 3 primitives were tested: circular patterns like circumnavigating a lander, raster scans for mapping, and arc trajectories for site-to-site travel. We used the Frechet distance to quantify trajectory similarity and tracked collision statistics to measure safety improvements. Our low-gain circular pattern showed conservative avoidance behavior. Path lengths increased from 59.7 to 62.6 meters with a Frechet distance of 1.3. We reduced large rock collisions from 3 to 1, though small collisions increased slightly. High-gain settings produced more reactive behavior. The reactional distance nearly matched nominal trajectory distance at 59.7 meters with a Frechet distance of 0.7. We eliminated all rock collisions and minimized the smaller ones. The higher gain settings is significantly more reactive to the obstacles and thus remains nominally closer to the reference trajectory. The raster pattern maintained its structure while avoiding all obstacles, with minimal deviations of 21.2 meters versus 20.4 meters, and a low Frechet distance of 0.6. The stretch version at the right shows scaling at different start and goal locations. Our arc pattern achieved the best performance with a Frechet distance of 0.5. The system eliminates all collisions while adding less than a meter to the overall path. This would nominally be used depending on the lighting conditions circumventing the lander. For more information about our autonomous excavation efforts, please check out the website at nasa.gov/ircu-pilot-excavator. Thank you for your attention, and I'd be happy to answer any questions sent to me.